Now we are going to study about potential difference in a uniform electric field. Before studying electrical potential, let me just revise with you in gravitational potential energy and gravitational potential. Now, in order to understand gravitational potential energy, you all are very well aware that suppose if there is a mass m at any height h from the earth, it will have a gravitational potential energy of mgh. But if there is no mass, then at this point where this mass exists, let us say that this point is point A. Okay, then at this point, which is, let us say this is point A, if there is mass, then there is gravitational potential energy which is given by mgh. But if there is no mass, still at this point from the earth, which is at a height h from the earth, it still has a potential which is called the gravitational potential, which is given by g into h, because the field, gravitational field, is given by g vector here and g vector here. So the gravitational potential energy is mgh and gravitational potential is gh, and there is no mass, no m needed to find out what is the gravitational potential. And if m is 0, the gravitational potential energy is 0, but you still have gravitational potential which is given by gh. This understanding is very important because it is similar in the electrostatic potential and electric field and electric potential. In a similar manner, suppose that there is a charge at this point, and the charge is q0 plus q0, and it is moving from this point A to B, and suppose this point is A and this point is B, and the distance moved is d. Then the gravitational potential energy will be minus q0 integral of E vector dot ds vector, from the basic definition of potential energy. So you'll have some potential energy difference when you move from one point to the other, which will be given by minus q0. Now electric field and displacement vector, they are parallel to each other, so it will be E ds cosine of 0, so it will be equal to 1, and integral, because electric field is uniform, so we can take it outside. You have a uniform electric field, so what you get from here is q0 E, and the total displacement is d. So there is a potential energy difference when you move from one point to the other, and the charge q0 is moving. But on the other hand, if suppose there is nothing here and this point is A, and again actually it's the same electric field and the same points, but in order to make it more simplified, I've drawn it in two different diagrams. So if you're moving from one point to the other by a distance d, there is no charge that is moving. We're just seeing what is the potential at this point, and you move to this point, and what is the potential at this point. So the electric potential is given by minus integral of E vector dot ds vector, even though there is no charge associated, no charge is moving. So if you calculate it, it will be minus ed. So the change in potential is minus ed, and change in potential energy is minus q0 ed. So if I write it as VB minus VA is equal to minus ET, and even this one UB minus UA is equal to minus Q naught ED. Then what information can we get from here? From this one we can say that the potential at A is greater than the potential at B, while in this case the potential energy at A will be greater than the potential energy at B. So there is a potential difference even though no charge is moving in the electric field itself when you move from the positive point of the electric field to the negative point of the electric field. These positive and negative, they just mean that they create the electric field. These charges, they create electric field. So when we're talking about the charge Q naught, it has nothing to do with these charges because they are used to create the electric field. Okay? And when a positive charge is moving from a point A to point B, then at A the potential is high and at B the potential will be low. So you'll have a higher potential at A and a lower potential energy at B. Similarly, when we're seeing the change in potential, then at A you have high potential and at B you have a low potential, and here it is high potential energy and low potential energy. Now let us see what will happen if the charge is minus charge. So let us say if it is minus Q naught, that is moving from point A to point B, and this distance is d, then the change in potential energy will be minus Q naught E vector dot ds vector. And as you know that the electric field and displacement vector, they are moving in the same direction. Therefore, the angle is 0. So it will be minus Q naught E into d. But the charge is a minus Q naught, so this will turn out to be plus Q naught. So it will be UB minus UA is equal to plus Q naught ED, which means that the potential energy at B will be greater than the potential energy at A. So if it is a negative charge, then it will have a lower energy when it is near the side of the electric field, and it will have a high potential energy when it will be away. But now if you compare these three, then you see that potential is independent of charge, so it has nothing to do with charge. Charge might be plus or minus. You always have a high potential near the plus plate and the low potential near the negative plate if the electric field is being generated by the plates. And if you're talking about the potential energy, it depends on the charge. If it is a positive charge, here you have a high potential energy, and if it is a negative charge, here you have a lower potential energy, which is also very well understood from this plus and minus, because it will be a low energy state because of the positive charge near this plate, and it will be high energy state because plus and plus, they will repel each other.